Hey, welcome back to Fan Mama Physics. This is example 2 in 6.1 part 2, vertical circles. In this example, we have a car driving up and down a hill in which the curvature is roughly in the shape of a circle, so we get a bit of a circular motion effect, so a little bit of centripetal acceleration depending on which part of the circle you are talking about. So in this case, notice that it might be a little bit different because the where you're sitting, where your object is in relation to the circle might affect which direction the forces are pointing, especially the normal force. Because take a look at the previous example with the skaterboard. When the skaterboard was at the top of the circle, he's going underneath the circle, which means that he's going to feel the normal force up against his feet, which normal force points towards the center of the circle. In this case, it might be a little bit different because take a look at this car over here in position C. The car, even though he's at the top of the circle, he is on top of the circle. So he's sitting on top of it. So his normal force might be pointing in the other direction. So even with vertical circles, you have to be very careful when you're drawing the free body diagram, which we will probably do first after we read the question. Okay, example 2. A 2,500 kilogram car is driving up a hill and passing the top. How fast should the car be traveling so that a 65 kilogram passenger feels weightless at the top of the hill? The second question is, how fast should the car be traveling at the bottom of the hill so the passenger feels 2 Gs? Ooh, 2 Gs. We'll talk about in a second. Okay, so I'm going to erase a few things here from the previous video so we have a little bit more space. Okay, the first thing we're going to do is we're going to draw the free body diagram on all of these cars, which will start with the car here at the bottom. Okay, so we are told the radius of the circle, so the curvature of the road. That way we can work out some circles there. So this car at B is going to first of all feel the effects of gravity, so Fg. He's also going to experience Fn due to being on top of the ground. For a position at C, he's also going to feel Fg because it's always pointing that direction. And of course, there's going to be some amount of Fn. How much Fn there is for both cases, we don't know. We will have to see, depending on what the question is asking. Starting with question A. How fast should the car be traveling so that a passenger in this car will feel weightless at the top of the circle? So that's talking about C. A person in this car is going to feel Fg and Fn due to the bottom of the seat of the car. Now, when the person feels weightless, what does that mean for Fn? If you think Fn is 0 for weightless, you are correct. So that means that the car is clearing the top of the hill with so much speed that the person in this case does not feel any weight at all. Okay? And which is kind of why if you go really fast, you kind of feel like you're flying off the top of the hill in a sense. But anyways, let's write our free body. Let's look at our circle first of all. When the car is traveling around the top, this is our circle. Okay. He is traveling over the top of the circle, in which we have this radius. Of course, my circle is too small. But anyways, we have to look at the car's centripetal acceleration directed towards the center of the circle, in which that is the case here. So when we write our Fnet equation for the centripetal acceleration, Fg is pointing in that direction. So Fg is positive. We would have to subtract Fn in this case. Actually, yes, I'll just write it in then. We have to subtract Fn because Fn is pointing away from the center of the circle. In fact, enough Fn is going to is pushing the car away from the center of the circle. Fg, which can only be so much, won't be able to. Well, I mean, there's a lot of factors at play. So we finished writing this equation out. This is going to be m times the velocity of the car's tangential speed across the top of the hill squared divided by r. This is almost kind of like the skaterboard, in which the there's depending on the speed of the car, that's going to change how much Fg and Fn is going to be. So remember when I just talked about how the faster the car travels, the lower the Fn is going to be. And that kind of makes sense, because if you take a look at it, Fg here cannot change, because that's just the weight, right? Weight doesn't change on Earth. Now, what could change is the speed. If the speed changes, that means this side of the equation will get larger, and the only way for this side of the equation to also be as large is to make whatever the Fg is subtracting smaller. So Fn has to be smaller and smaller and smaller to a certain point in which the speed is so great that the person does not feel any weight at all. Remember, feeling the weight is different than having the weight. Feeling the weight is your apparent weight that is characterized by the normal force, not Fg. That's the actual weight. So for weightlessness, this has to be 0, in which we just have a simple case in which Fg is equal to mv squared over r. So let's write that here. mg equals mv squared over r. Okay, because Fn went away, Fg is just mg, and we want to cancel the m's. Okay, let's cancel the m's, because the mass is the same. We want to find what? The speed. Perfect. So then we just rearrange this by multiplying r on top. That gets rid of that. And we're going to get v squared is going to be rg, and which all we need to do is just take the square root of both sides, which we are going to get the square root is equal to the radius, which is 200 meters, times gravity 9.81. Okay, and that's going to give us 44, okay? 44.29, and that's going to round up to 44 meters per second. Oh, how much does that in kilometers per hour? That's whoa, 159 kilometers an hour. That's speeding. Speeding very much. So notice it didn't really matter the mass of the car, it didn't matter what the passenger was. It only depended on the nature of the hill and the acceleration due to gravity. Okay, next up we have B. How fast should the car be traveling at the bottom of the hill so the passenger feels 2 Gs? Whenever we say 2 Gs, 3 Gs, 4 Gs, half a G, that is that's the apparent weight associated with what gravity would be. So 1 G would be 9.81. So right now I'm sitting on my chair. I am feeling 1 G. Okay. If let's say I'm on an elevator, or maybe on a amusement park ride, which I am lifted upwards at a very lifted up very suddenly. So for here we go on maybe you've been on the elevator, maybe you've been on something where something just shoots you up. Okay, and if that were the case, sometimes it might accelerate so quickly that you may feel 3 times your weight. You might feel 4 times your weight. And whenever we say you feel 3 times your weight, you're feeling 3 Gs. You're feeling 4 Gs. Okay, so that's just related to the apparent amount of gravity that would need to be acting on you in order for you to feel the normal force being that large. Okay, so for 2 Gs, how would we solve this problem? How would it look like on paper? First of all, we have to draw the free body diagram and to identify which circle we're talking about. So here we have a car on the bottom of the hill, and which this is the circle. Okay, and the problem even traced out the radius for you, so you can actually figure out the circle yourself. The acceleration is directed towards the middle, or towards the center of that circle, in which when we write our F net equation, it's going to be the normal force, because that's what's pointing towards the center of the circle, minus the Fg, because Fg is pointing away from the center of the circle, and that's going to equal to mass times the velocity of the car divided by the radius of the circle. So let's put this into perspective a little bit. We know that Fg doesn't change. We cannot change that. But we can change the normal force. Normal force is relative to how fast or the acceleration or whatever. So let's imagine this car is going really fast through the bottom. If you're going really fast at the bottom, the only way you're going to make this part of the equation really big. Since Fg cannot change and F normal is the only one that can change, if this side of the equation gets really big, Fn also has to get very big. And if you kind of relate to a little bit, because imagine, think about a roller coaster that you've been on. Maybe think about the time where the roller coaster came down and then it kind of shot back up again. So at the very bottom of that roller coaster where he kind of climbed back up, so you probably are going really fast. Right? If you're going really fast through the bottom, you're going to feel really heavy at the bottom. Your Fn is going to be very large. And this is kind of like what this car is doing. It's going through clearing the bottom of the hill at a very large speed so that for you, you're going to feel heavier. And how much more you're going to feel heavier? You're going to feel 2 Gs heavier compared to before. 2 times your normal force. Okay? So how do we put this into the equation? How do we substitute these G's into the equation? So imagine, so remember when I talked about how heavy you feel will be normally, okay, let's say you're sitting on a chair or something, okay? If you're just sitting on a chair, nothing's happening, then your Fn is going to be equal to your Fg. We say you're feeling 1 G. I'm feeling 1 G right now. If you're feeling 2 Gs, you're feeling 2 times your weight. I'm actually going to say 2 times your actual weight because normally we feel our actual weight. Normally our apparent weight is our actual weight, but that can change depending on how fast, which direction, and how we're moving. So if we're feeling 2 Gs, then we're going to say, okay, our normal force that we're feeling right now is going to be equivalent to 2 times our actual weight. So 2 times our Fg. And so that just means that your normal force at that time is twice your actual weight. You feel double your weight. Okay? 3 times 3 Gs will be 3 times your actual weight. 3 times how normally you would feel. Okay? So if I have to rewrite this Fn, and in terms of the passenger feeling 2 Gs, I'm going to say that this Fn is now 2 times Fg because this passenger is feeling double his normal weight. And I continue writing the rest of this equation, which is minus Fg here equals to mv squared over r. You might be thinking, if I'm feeling 2 Gs already, why do I have to do this? Okay, this equation has nothing to do with, this whole equation has nothing to do with how you feel. It's just the direction of the vectors and the forces and how they give you a centripetal acceleration. What we're talking about when you feel, that is Fn. So don't forget how heavy you feel is this Fn force. Okay, so if your Fn, normally your Fn is equal to your Fg. Okay, so if that's the case, if Fn is equal to Fg, then this whole thing is 0. Okay, this whole thing is 0, meaning there is no centripetal acceleration, meaning that there's probably not much curvature to the ground. But because there is some curvature, we might experience some a larger value in Fn because we're going through the bottom faster than normal. Okay, so keep in mind, Fn is just what you feel. So if I write this one out, this is going to give me, this is mg, so I get 2mg minus mg is equal to mv squared over r. The m's do cancel out, so I'm going to erase this for now. So we're going to simplify this. This is just going to be, well, first of all, we know the m's cancel out, so this kind of goes away. We are then left with 2g minus 1g is going to give me 1g is equal to v squared over r. Huh. Isn't that interesting? Because that just looks like the top, really. This just looks like this top over here. So if I just do that, I rearrange the equation, I'm just going to get v is equal to square root of rg, and that's just going to give me 44 meters per second again. So that's interesting. It just so happens that the speed of which this car clears the bottom, making the passenger feel twice the weight, is exactly the same speed that the car needs to clear the top in order for the passenger to feel weightless. Interesting, hey? Okay, so, whew. I don't know, how complicated was that? Was that tough? Hopefully it made a little bit of sense after looking through the solutions to this example. And I have banked questions coming up next. So thank you for watching. I wish you good luck. Fam Physics signing out.